Okay, so we move on to the next regular talk, which is about continuation of symmetric periodic orbits in the Sitnikov problem. Ortega, GALAN VIOQUE. And again, I will raise my hand if I will have 5 minutes to the end.
So, thank you very much, and thank you for being here and for the opportunity of talking about this project. In the first talk, we have learned that in celestial mechanics, very often you have many bodies, and there are some interaction that leads to some binary states in the temporary position, in a temporary state. Well, this is an example of that. I will show you some results about our joint collaboration with Daniel Núñez and Andrés Rivera, who for some time stayed in a binary state with Rafael Ortega in Granada while doing the PhD. Then they escaped from Granada and make a short stay with me in Sevilla. And after a number of years, they joined in a faraway place in Colombia, and they made a more or less stable binary state. Well, they have a very active group in dynamical systems, mainly in celestial mechanics. And to close the circle, there's a young satellite who is Camila Riccio, who escaped from this state and hopefully will make a long stay while doing her PhD in Granada again. So you will see that there's a kind of recurrences in this problem. I will show you some results on a very old problem. My main specialty is continuation of periodic orbits in symmetric systems. For some years we have been working in problems related to n-body problems with some collaborators in Sevilla and some other places all over the world. We develop a technique to continue solutions where you have several parameters. They could be internal parameters like the energy or the angular momentum that we heard in the first talk, or they could be just explicit parameters. In our case, the Sitnikov problem is very well known to all of you. It's just two bodies in a Kepler orbit and a vertical, and a small body moving in a vertical line. We have these two kind of parameters: the energy, which will be represented by the initial condition, and then we have the eccentricity of the two bodies. And we'll see what happens to the dynamics when you change both of those parameters. Well, the examples that we have been working in the past years were autonomous systems. We did not have an explicit time dependence. And then for some time we did some work in a different problem in which we had a parametrically excite system. It was a collaboration with some people in Bristol, and we learned how to do this continuation of solutions in the presence of this non-autonomous character. So, well, we have been, in particular the two researchers in Colombia, they have a long experience in the Sitnikov problems, and as I told you, the two parameters that we will move is the initial condition of the massless body in the vertical line, and then the eccentricity of the two primaries. And there are some old and not so old results on the classification of the families and the bifurcation behavior, and in particular there is a very interesting paper in Science in which Llibre and Rafael Ortega, they prove several things about the existence of these branches and how long they could be extended in the eccentricity, what they call the global continuation, and we will have a look at those kind of results. These are the equations, which are, well, I just want to draw your attention to this term here, which is time dependent. So this is a non-autonomous second order differential equation, and we have the dependence on the eccentricity and the initial conditions. So as you change the distance of the massless body in the vertical x, you change the energy, and as the energy is conserved in the motion, well, it's not conserved because it's not autonomous, but anyhow, you will change the initial condition by starting from the body at zero velocity. Well, you all know that the way this distance of the primaries change, this RT, is you have to solve Kepler's equation, which is an implicit equation, and well, there are some properties that you have to take into account when you're doing the continuation. We will see that if you start from such initial conditions, the solutions are even in time. And that will be important in the rest of the talk. And there is a parameter here which is an integer, which is capital N, which is how many revolutions of the primaries you allow. And we will classify the solution by this N. We will just consider increased values of N. These are some very low quality figure taken from the paper by some people in Mexico, and they show the branches and families and bifurcation of the families as you change the initial conditions and the eccentricity. And because we will have a look at this paper the other way around, we just rotate it and reverse, and you will see that in the vertical axis I will use the initial condition, the initial position, and in the horizontal one the eccentricity. And we will focus mainly on these first branches. So I will just try to say something about how these branches are born, about the stability, linear and non-linear stability, and forget about the rest of the figures by now. As I told you, we will fix the number of revolutions of the primaries, which is this capital N, and we should bear in mind that there is a time dependence in the equations. This is a schematical picture taken from the paper by Ortega and Llibre, and they show the proof that starting from this circular solution, there are only two possibilities. Either the branches extend up to eccentricity close to 1 by the collisions, or they could connect to the equilibrium solution, in which you have no distance to the plane of the primaries, and you just change it as eccentricity. And there is a well-known limit to the number of branches that you could expect just by fixing the capital N. And this is just this new number here, which tells you how many branches you will find. And these branches will be classified by the number of zeros that you have in the movement of the primary, of the small particle. Well, the first thing is, if we want to say something about the stability, we could try to compute the determinant of the monodromy matrix, which is called this delta function here, trace of this function, and this will tell you whether the system is stable or unstable. So in principle, just by looking at the circular solution with zero eccentricity, you could in principle say if the branch is going to be stable or unstable. And well, they did this computation, the people in Colombia, and they just computed the slope of this delta function. So just by looking at this slope, if you start, well I did not say, but you start from a very particular initial conditions, all these branches are in the parabolic state. So the multipliers are at +1. This is at the beginning you don't know whether you will go to stable or unstable, depending on the sign of this quantity. Well, the ugly thing is that you have to compute several quantities, which will appear more in the talk. This n and different expressions are not so easy, several lines of expressions, but the thing is that everything depends on just the fundamental solution of the variation equation. So in principle, these quantities are computable. You can say what is the sign of this delta function. Well, the bad news is that in the low values of n, this slope is 0. So you cannot decide whether the system will be stable or unstable. The first part of the project was just to rigorously prove the extension of these branches, and they did some quantifications of the branches, and this has been published this year in Science. I'm not going to get into the details. It's a very technical paper, mainly done by these two researchers in Colombia, and they're able to prove and quantify these branches. They were very happy because they were able to say up to which value of the eccentricity it is proven to exist. We would like to say something about the stability, and in particular, in the last part of the project, we will have a look at the twist coefficient of these branches. So once we know that it's linearly stable, we would like to say something about the nonlinear stability. And this is work in progress. I will show you some results at the end of the talk. This is the table where you can see how many branches you have to look for each value of the n, and I can show you that I can tell you that there are results only for the first values. To start the branches, you need a nonlinear center. You need an equilibrium position, which is a center, and the important thing is that the period should be a monotonous increasing function. So just by fixing the value of n and by looking at the intersection with the horizontal line, you know where to start the branch. This is just a straightforward computations, and you see, for instance, for n equal to 1, there are only 2 starting solutions. And we take this as initial conditions, and now we do the continuation in eccentricity. So in the first place, we will do continuation in the energy by going through this nonlinear center. And once we know which are the special solutions, we can do a parameter continuation in eccentricity. That way we get these branches. And here we found a problem, that if you look at the slope of these branches in this axis, which is the initial condition and the eccentricity, they seem to go down. So they have a decreasing character. In the first pictures I show you, they are going up. So this is kind of puzzling. We were not sure whether we're doing things right. So in a few slides I will just tell you the end of the story. This is how the solutions look like. This is p equal to 1, in which you have just one crossing of the axis as you in half a period. And this is the second branch. Just to see you that you can have a look at the solutions. And this is the more important thing. We have a full control of the branch, and we can see what happens to the linear stability. So this is the plot of the logarithm of the multipliers. So every time you have a 0, that means that the multiplier is +1, and it's stable. So we have a long interval of eccentricity in which the solution is linearly stable. At this point, we have a period doubling, and we know that because if we look at the argument, which is just the angle of the multiplier, we know that it started at 0, which is a parabolic state, and then they evolve along the unit circle until they reach -1, which is pi. So this is the period doubling bifurcation, and we have a full control of this multiplier. And on the bottom picture, I show you the functions that tell you whether the solution is stable or not. And as I told you at the beginning, the slope of this function is 0. So you cannot say, just by looking at the beginning, whether it will go inside this -2 region or outside. So we cannot decide just by looking at the slope whether it's stable or not. And this is the same for p equal 2, and this is a general result. Most of the solutions that we have looked at are linearly stable, and they extend the stability up to very high values of eccentricity. In this case, up to 1, up to 0.9. So stable almost all the region of eccentricity. And again, the slope of this determinant function is 0. So we cannot say just by looking at the first derivative whether it will be stable or not. This is just the same graph in the whole eccentricity region, and you see that it looks like it's going to, well, connection of the 2 branches, but this is an active end. I just show you only one parameter here. This is not a problem at all. Well, we had numerical evidence just by looking at the multipliers and by computing this determinant that the slope is 0. So at some point we thought that maybe we can do a continuation in the eccentricity to negative value. Well, that in principle is nonsense. The eccentricity should be positive. But if you look at the equations, you can treat the eccentricity as a real parameter, and there is no problem in principle to compute to negative value of the eccentricity. And when you do that, you see that this is like a parabola shape, and you can see that if the solution is even, well, you have a proof that this first derivative should be 0. Well, that's what we did. And for some of the branches, we managed to have numerical evidence that this determinant function is even. So we have a way to decide under which condition this derivative should be 0. And Well, the thing is that we were able to analytically prove that only for odd values of n. And that's kind of weird because for most of the branches, n equal 1, 2, 3, and 4, we found that this is a, well, in case we only found one case in which this is not true. But we were able to prove it only for odd values of n. This is just a summary of the theoretical results. In the quantification of the branches, they were very happy because just by comparing the solutions to the equilibrium solution, the one which is close to the origin, they were able to prove that the branches should exist at least in this region of eccentricity. And when they showed me this number, well, I told them that they could be very happy with the theoretical result, but this is something that's very difficult to compute. And the problem is that they were comparing with a solution which is very far away from the branch that they are looking for. They should have a very more refined way of doing the quantification, so they went back to the pen and papers investigations, and they were able to improve quite significantly the values of the critical eccentricity. And at the end, they were able to compute something which is more or less computable. If you're working with computers, you know that 10 to the minus 16 is more or less the precision of the calculations. If you tell me that I have to look something in the 8 decimal place, I can do that. If I have to do that in the 14 decimal place, then I have to go to extended precisions. Probably it will be a very hard task to do. So the thing is that the existence of the branch was proven in this interval, although we know that it is extended to much higher values of eccentricity. And this is the comment I made, that we were able to prove that this determinant function is even only for odd values of n. And all the solutions we found for these even solutions in time were stable. Only one solution turns out to be unstable. And we know by the big results that there should be as many stable and unstable solutions. So somewhere there should be some unstable periodic solutions looking for us. This is just to convince you that these local results are valid over a long range of eccentricity. In blue, you have the actual branch computed for n equal to 1, and in green, we have the linear prediction. So if you just compute by the implicit function theorem, and just by looking at the solution for the circular problem, you can see that the linear prediction, which they prove to be valid only for 10 to the minus 8, you can extend it very safely up to 0,1 in eccentricity. So you can say many things about what is happening for higher values of eccentricity just by looking at the way that the branch is born. And this is almost my last branch. The work in progress that we are working now is, once we know that the solution is elliptic, we know that the multipliers are on the unit circle, we would like to say something about the nonlinear stability. So Daniel Núñez made a visit to Sevilla last spring, and he told me that we should have a look at the Birkhoff coefficient. Well, and then, that's the recurrence result I was saying at the introduction. We went back to some rather old papers by Rafael Ortega, in which he shows that the Birkhoff coefficient is explicitly computable by using this stability by the third approximation, which is just a look at the Taylor expansion of the going beyond the linearization in the stability properties. And well, there is an explicit expression that you could in principle compute on the branch. There are some quantities here, this capital N, this capital A, this capital C, which are very long expressions. But the thing is that all of them depends just on the argument of the multipliers. The first picture I show you with the log of the Fourier multipliers and the argument. This theta here is just this argument. So if you know where you are on the unit circle, you can compute this lambda, and you can, in principle, compute this beta of E, this first Birkhoff coefficient. If this coefficient is different from 0, you know that there is a twist condition, and you have, yes. And the thing is that there are two technical difficulties. One of them is very easy to, if you do some work, you can forget about this, is that this result is only valid for monodromy matrices which are a pure rotation, and there's some technical details that I can show you. It's called R ellipticity. This can be overcome. You can do that. But this is not so easy. The solution should be elementary. Full elementary means that you have to avoid the strong resonances. And the problem is that the branch here is parabolic. So you are close to one of those solutions that are not included in the validity of this expression. So here's the point where we are, and I expect to get some feedback from you and see if we would, in principle, expect to compute the Birkhoff multiplier and then go to the E equals 0 case. Thank you very much.